So this sums up our discussion of electrostatic interactions, at least the classical types. And we can move on to the two remaining types of non-covalent interactions, the van der Waals and nonpolar interactions. So let's start with the van der Waals. Actually, the basis of this type of interaction is also electrostatic, but it's very different from what we saw before. In the previous types that we discussed, the interactions were based on fixed charges, whether they were full charges or partial charges, but they were fixed. Here, we have an interaction between transient charges, partial transient charges, and these charges form inside a single atom, not over a whole chemical group or a chemical bond. So what happens is that if we look at a single atom, it has electrons around the nucleus, and these electrons are distributed in various parts of the atom. However, due to quantum fluctuations, at some point, the electrons concentrate on one side of the atom. And this builds a dipole between this part of the atom, which is partially negative, and the opposite side, which is partially positive. So when this happens, and the atom is close enough to another one, it induces the same dipole in the other atom. And this allows the two dipoles to interact in a dipole-dipole interaction. So this part is called, this is called the attractive component of van der Waals interactions, or dispersion forces, it's another name. The energy of the van der Waals interaction can be seen here in this empirical plot that is obtained by experiments. And the equation here, which is its mathematical representation, it's called the Lennard-Jones equation. So if we look at the plot, we see that the vertical axis, the horizontal axis, sorry, is the distance between the two atoms, and the vertical axis is the energy. And if we start at this point, this is where the atoms are very far from one another, 8 angstroms. And at this point, they don't have any interaction occurring between them. We can see that the energy is indeed 0. But when they start to get closer to one another, they start to attract each other, and the energy becomes negative. And it drops up to a certain point where it is minimal, and the attraction is maximal. But if the two atoms keep on going closer and closer, they start to repel each other, and this is seen by the sharp rise of the energy. So this part of the plot is called, it's the second component of the van der Waals interactions. It's called the repulsive van der Waals interactions. Again, this Lennard-Jones equation describes the plot, where the left component describes the repulsion, and the right component describes the attraction. And we can see that, as can seen in the plot, the repulsion is much more steep than the attraction, and which means that this type of interaction is more short range than the attraction. But even if we look at the attractive component, it's also very short range compared to other types of interactions that we've seen. Certainly the ionic interaction, but it's also much more short range than hydrogen bonds, in which the R factor was raised to the power of 3. Here it's with the power of 6. Now, if we get back to this point, as I said, this point signifies the distance in which the interaction between the attractive interaction between the two atoms is maximal. But it also signifies the point beyond which the two atoms cannot go closer. And this helps us to represent bonds more accurately in the literature. We often represent atoms as spheres, as we can see here, the carbon atom, which is a part of this molecule. And when we do that, we use the van der Waals distance, which is this point of minimal energy. We use it as the radius of the sphere. to signify the boundary of each atom, because we know that this is the boundary because another atom cannot get closer to this atom beyond this van der Waals radius without forming a chemical bond. Moving on, we get to the last type of non-covalent interaction, which we'll discuss, called nonpolar interactions. We saw earlier that electric charges have a strong preference to be surrounded by water, and that's because they contain, because they can be masked by the water molecules around them. And we even calculated the energy penalty that involves the transfer of a charge from water to a nonpolar medium. We saw that that this energy penalty is a few dozens kilocalories per mole. So molecules, for that reason, molecules that contain charges, whether they are full charges or partial charges in the form of dipoles, such molecules are referred to as hydrophilic, which means loving water in Greek. But when we look at biological systems, we can also see the opposite example. We can see molecules that prefer to be inside nonpolar media. And that's because they don't contain charges or even partial charges in the form of dipoles. And therefore, when they are in water, they cannot be masked by water molecules. So these molecules are referred to as hydrophobic, which is fearing water in Greek. And as I said, they prefer to be in nonpolar media than in water. But when we do put them in water, we can see an interesting phenomenon. We can see that they tend to huddle together and form aggregates. And the physical basis for this is what we call nonpolar interactions. And we should know that this name is a bit misleading because this phenomenon does not result from an actual interaction like the ones we saw earlier. It actually results from an indirect effect that we call the hydrophobic effect. And to understand it, we must first talk about water, about pure water. In pure water, the water molecules can form hydrogen bonds with one another. We saw this in one of the previous slides. But still, they are free to move around and rotate and so on. And this means that they have a high entropy. Entropy, we haven't discussed it yet, but it's a physical quantity that has to do with the degree of disorder of a system. Or in other words, when we talk about a system that contains molecules, then the entropy has to do with the different ways that the molecules can rearrange in space. And when if we come back to water now, if we look at the individual water molecules, in pure water, they can move freely, like I said, which means that the system has high entropy because the molecules can rearrange in different configurations. That's what happens in pure water. But what happens when we insert a nonpolar molecule inside the water, or as in this case, a molecule that has a large nonpolar group, a benzene ring? In this case, since the benzene ring does not contain strong charges or dipoles, the water molecules around it cannot form hydrogen bonds and mask and create favorable interactions. What happens instead is that some of the water molecules around this group form an ordered structure, which we call a cage or a cluttered cage. And that's a problem because in this context, in this cage, the water molecules cannot move freely. They form strong hydrogen bonds with one another because they can't form hydrogen bonds with the group, and they do not move freely. And that's a problem because if we go back to the concept of entropy, the second law of thermodynamics tells us that in the universe, spontaneous processes involve an increase in entropy. And here we have the opposite phenomenon. We have a decrease in entropy because the water molecule become engaged in this cage structure, which means that such a process cannot be spontaneous. It is energetically unfavorable. So this happens in the case of this molecule that is inserted inside water. And if we insert a second nonpolar molecule, the same happens again. So the decrease in entropy is now even double. So what happens next is that the two nonpolar molecules can move inside water, and sometimes they can huddle together and become close to one another. When this happens, the water molecules that were between them are released into the bulk medium, and now they regain their original freedom of movement. So this means that if two nonpolar molecules get close to one another and form an aggregate, the bulk water around regains some of its entropy or restores some of its entropy. And therefore, this process of nonpolar molecules getting close to one another is a spontaneous process. And this is the hydrophobic effect, which we sometimes call nonpolar interactions. This is the effect that accounts for nonpolar molecules joining together when they are inside water. Now, the energy of this interaction cannot be described accurately because, as I said, this is not a physical interaction per se. But we do know that the energy correlates with the surface area of the nonpolar groups that becomes buried when they interact with one another. This is delta SA. And the correlation is the correlation factor is this number here. So we can use this equation to get an estimate of the energy of the nonpolar interaction if we know the size of the surface area that becomes buried. And we have an example here. We have two molecules that contain nonpolar groups. They are inside water. And when they get close to one another, which looks like they're interacting, but again, this is not a physical interaction per se, it's the water driving them together, then if the surface area that becomes buried is 14 angstrom square, we can put it in this, we can solve this equation by multiplying this number with the prefactor and get the energy of interaction, which is in this case, minus 0.35 kilocalories per mole. So again, this is not an accurate calculation, but it's a way to estimate nonpolar interactions. So that's it about the hydrophobic effect or nonpolar interactions. And here we have this table, which again summarizes, this is from the book, summarizes all the equations and the parameters used to calculate or to estimate the energies of the different interactions that we went over. We can now conclude chapter 1. We saw that macromolecules are important for life processes in all living organisms, that proteins are the most functionally diverse types of macromolecules, and that their functional diversity results from their chemical and structural complexity, which is based to a large extent on their ability to form versatile binding sites to other molecules. We also saw that whereas the chains of proteins are constructed by forming covalent bonds, which are strong, the folding and binding capabilities of these chains rely on much weaker non-covalent interactions. We saw that most of these interactions are electrostatic in nature, but at least one of them, nonpolar interactions, are different. They result from the hydrophobic effect, which in turn has to do with the entropy of the water solvent that, in which the proteins reside.